Okay, in this lecture video, we're going to finish up the reactions of alkynes and talk about addition reactions to the alkynes. Now, remember from the last lecture video, we talked about a carbon-carbon triple bond having basically one sigma bond and two pi bonds. So, in this case, that means that for the most part, the reactions that a triple bond undergoes are the same as what a double bond did, except that we have two pi bonds, and so this can act actually as an electrophile twice. So here are the lists of the reactions with, for instance, HX, HBr, HCl that we talked about with double bonds. And so these reactions still follow the Markovnikov's rule. In this case, it'll only follow the Markovnikov's rule if it's a terminal alkyne. If it's an internal alkyne, then you're going to get a 50-50 mixture of the products because there won't be a Markovnikov product. So there can only be a carbon with the most number of hydrogens if it's a terminal alkyne. But for the sake of argument, let's start with that. So if you add one equivalent of HCl, HBr to the triple bond, we're just basically going to we're going to add H and the Cl or Br Markovnikov to form the double bond. Because one of the one pi bond and the triple bond will then become a double bond. We can do anti-Markovnikov addition using adding HX with peroxide. This would go through a free radical mechanism, and we would add the H to the carbon with the least number of hydrogens and the X, the halogen, to the carbon with the most number of hydrogens. So this right here would be an anti-Markovnikov addition. We could add two equivalents of HX, both Markovnikov, in which point you would add HCl or HBr and a second equivalent so that you would end up with our geminal dihalide. In the last lecture video where we talked about forming the triple bonds, in the synthesis we said that we could form a triple bond from a geminal dihalide. And at that time I mentioned, well, yeah, the problem is that the geminal dihalide has to come from a triple bond, and this is how we would form it. So we would add two equivalents of HBr or HCl, and then do the Markovnikov addition basically twice. And if we used a halogen then and reacted it with the triple bond, the halogen like Br2 is typically what we would use. Br2 would add trans to the double bond, and basically you could imagine this going through a through a bromonium like intermediate, as we saw with the double bond itself. So all of these reactions are basically the same as what we saw with the double bond, except that we would have the addition of up to two equivalents of that reagent. So let's do a couple of examples here. So let's take, for instance, let's take an internal alkyne and let's add an HBr to this. Now in this case, in the internal alkyne, there is no Markovnikov product because both carbons have the same number of hydrogens attached to them, which is 0. So if this is an unsymmetrical alkyne, meaning that there's different groups attached to the triple bond, you would actually get a 50-50 mixture of products. So I would add the H to the carbon, let's say on the left, get a double bond, and then add the Br to the carbon on the right. And the intermediate in this case, if we think about writing sort of an abbreviated mechanism, the triple bond would be used to bond the H+. Right, if we added it to this carbon, we would end up with this carbocation. And you can imagine that then the Br minus would add to this side or to this side, so that for that product we would actually get a mixture of these are year Z. So in this case, this would be the bromines, the high priority group between bromine and methyl. Ethyl versus hydrogen, ethyl wins, so this would be the Z, and then this would be the E isomer. So we would get a 50-50 mixture for adding the hydrogen and basically forming a secondary, well, it's a secondary vinylic carbocation. But you could also imagine adding the H plus to the carbon on the right, where we would then form this secondary vinylic carbocation, and then again the bromine could come in and add to this side. It could add to that side, so that we would end up with the CH3, CH2 with the bromine bonded here. And it would also end up with that as my other product. So in this case, bromine versus ethyl, bromine wins. Methyl versus hydrogen, methyl wins. This is the E isomer. And then over here, bromine versus methyl, methyl versus hydrogen. This is the Z isomer. So these reactions of internal alkynes with something as simple as HBr become really, really, really messy. Simply because there is no Markovnikov product, so you would get a mixture not only of the two products that were basically regioselective, or dealing with regiochemistry in terms of adding the carbon to the middle carbon, adding the hydrogen to the middle carbon, or adding the hydrogen to the carbon on the right. All four of these products would basically be formed in roughly about 25% yield, so they would be roughly the same. So in this case, there is no regioselectivity and there's no stereoselectivity to that reaction. And then you can imagine that if I formed these two sets of products and now I added a second equivalent of HBr, that second equivalent that I added would create all sorts of havoc, because now I'd have to add the HBr. And in this case, with these two products, I do have a Markovnikov product now. And in this case, I would also have a Markovnikov product. But I would end up with, in this case, adding another equivalent of HBr. What would I end up with? Actually, over here, I would add, for the top one, I would end up with the same product, right? Because if I added the next equivalent of H plus to this double bond, I would add the carbon, I would add the hydrogen to this carbon, and then that's going to leave this carbocation that then the Br minus would come in and add to. So for the top pair of products, I'm going to just end up with one CH3, CH2, CH2, and then a geminal dibromide. So that would be the product of the first reaction, and then adding HBr to either of the E or Z of the second addition product, I would end up with adding the H here, I would end up with this carbocation, and then the Br minus would come in and add to that carbon. So this would be the second product formed from the second set of EZ products. So if we added two equivalents, we would end up with two basically geminal dibromides, but they would be ultimately ended up adding the hydrogen to the carbon on the right or the carbon on the left. So that's just one example of adding two equivalents. For the bromination, let's go back to this and talk about that mechanism. So if I was to take that CH3, that internal take that internal, or sorry, this is a terminal one, but it would work for an internal as well. If I add the Br2 to this molecule, what happens is the pair of electrons goes to bond the bromine, kicks off the bromine. So then I would end up adding the bromine here, having my double bond. And what I would actually end up with is the bromine then bridging over both of the carbons, so that then when the Br minus came in and added, in theory that bromine would add to the carbon that is most substituted. Then what I would end up with is the bromines then adding trans, or in this case this product would actually technically be the E product. If I added another equivalent of Br2 to this molecule, if I then said, well, let's take that molecule and let's go ahead and add a second equivalent of Br2, what would I end up with? I would actually end up with two bromines on the carbon to the left, and I would end up with two bromines on the carbon to the right. So I would end up with a tetrabromo propane in this case. So I end up with two geminal carbons. So you can add one or two equivalents. I'm going to have to specify what you would do. Over here, as far as the peroxide anti-Markovnikov addition goes, not only would I add the H to the carbon with the least hydrogens and the bromine to the carbon with the most hydrogens for anti-Markovnikov, if I did a second equivalent, if I added a second one, notice that this is going to get really messy because now each one of those two carbons has the same number of hydrogens. And so if I added an HBr to this molecule, I would get a mixture of both adding the bromine to this carbon and also adding the bromine there. So that gets really messy as we add more than one equivalent of the HBr and anti-Markovnikov addition. So with the addition of just a second pi bond, that means we can do twice as much stuff here. Now, as far as a new kind of reaction that isn't really new would be oxidative cleavage. Now, we typically don't do, we typically do not do ozonolysis on the triple bond. And the reason is that because this triple bond is very stable, I've got to break, in order to cleave this, I got to break a sigma bond and two pi bonds, not just a sigma bond and a pi bond. So that means to cleave this, I'm going to need the strongest oxidizing reagent that I can find. And so in this case, typically, if we're going to do this reaction, we're either going to use KMNO4 and H+, but we're going to need to do heat. So we can do it with H+. We could also do it with OH- because the addition of heat with OH minus is basically going to cause a cleavage reaction to occur. And if you're going to do this by ozone, and again, typically we don't necessarily do this, but if you're going to do this with ozone, you need to do hydrogen peroxide. You might even need a little bit of heat there. So in terms of using these super strong oxidizing conditions to cleave the triple bond completely, if you think about our process from before, what I would do is I would replace the carbon-carbon triple bond with then the two carbon-carbon oxygen double bonds. And because there's no aldehyde or ketone formed, each one of those would then simply become a carboxylic acid. So whenever you oxidize a triple bond, you're always going to end up just with the carboxylic acids directly. Now, if you oxidize a terminal, if you do oxidative cleavage on a terminal alkyne, we're going to split this apart and we're again going to make our carbonic acid. And the carbonic acid then breaks down to CO2 and water. So one of the tests, if you have a triple bond and you wanted to know whether it was an internal or terminal, would be to add, for instance, KMNO4 with acid and apply a little bit of heat to it. And if you saw the fizzing of the carbon dioxide of the breakdown of the carbonic acid, then you would know you had a terminal alkyne versus an internal alkyne. And we'll talk more about that in the second semester, because basically those are what are called qualitative organic tests. And they used to be done routinely before the advent of spectroscopy and available spectroscopy techniques, which we'll talk about in the second semester lab course. So oxidative cleavage just has the wrinkle to it that we need to use the strongest oxidizing reagent available. Now, in terms of reduction reactions, and let me just go back here. Remember, oxidation means adding oxygen to the molecule in this case. So these are oxidative cleavages because I'm adding oxygen to the molecule and I'm cleaving the triple bond. So that means there's also reduction. So how do you reduce a carbon-carbon triple bond? Well, reduction means adding hydrogen. And there's three ways that we can do this. The first is to use hydrogen with palladium and platinum. So we're going back to our hydrogenation reaction. And what we have to realize is that when we add hydrogen, we're always adding excess hydrogen whenever we do any kind of hydrogenation reaction, whether it's with a double or a triple bond. We can't just add one equivalent of hydrogen. And even if we could, the first hydrogen would react with the palladium platinum metal catalyst, and what would it do? It would add the two hydrogens to the triple bond, and it would form, in this case, it would form a cis-alkene. But if we use just one equivalent of hydrogen, what would happen is that hydrogen would react with the triple bond. Some of that would be converted to a double bond, and then some of that double bond would react with the hydrogen and palladium and platinum to form the alkane. So we would get a mess of different products simply because one equivalent of hydrogen is going to react with each one of these molecules. So we would end up with some triple bond and some double bond unreacted. Now, that's why we use an excess of hydrogen, but if we use an excess of hydrogen with palladium or platinum, once we form the alkene, the cis-alkene, then the extra hydrogen reacts with it and takes it all the way down to the alkane. So typically what we do is just use excess hydrogen and do a hydrogenation all the way from the triple bond down to the single bond. Which leads to a couple of questions is, what if I want to stop at the double bond? What if I want to form the cis double bond? Well, what I need to do is I need to poison my catalyst. And so instead of using just platinum or palladium metal, we can use what's called Lindlar's catalyst. And Lindlar's catalyst would be to take the hydrogen gas and use it with a poisoned metal catalyst. So what they do is they take the palladium and add to it barium sulfate, some quinoline, and there are other molecules. If you look in the textbook or online, there's various formulations of this. But the idea is that what I did was I made my palladium metal less reactive as a catalyst. And so what happens then is that this poison catalyst cannot react with the double bond. So in this case, I just add one equivalent of hydrogen to the triple bond to form this cis double bond. And so the Lindlar catalyst allows me to form the cis double bond by, again, using a less active catalyst. Now, then the question would be, but what if I want to form the trans double bond? And if I want to form the trans double bond, I can't go through this hydrogenation mechanism. Because remember, the hydrogen gas comes and it sticks on the surface of the palladium, and then the carbon-carbon double bond comes in, and both hydrogens add at the same time. So I can't use a hydrogenation with a metal catalyst reagent. I have to go to a completely different reagent. And the reagent that I would use then, and this diagram just shows you the idea of the partially poisoned Lindlar catalyst. If you want to form the trans double bond, then you need to use what's called a liquid ammonia, because this ammonia is actually in its liquid form, and sodium metal, do a sodium metal liquid ammonia reduction. Now, this is a very, very old school way of doing this. What happens in this reaction is, first of all, ammonia liquefies at about minus 35 degrees Celsius. So it's very easy actually to make liquefied ammonia. You just take ammonia and you basically can put it in dry ice. Dry ice is solid CO2, and solid CO2 has a sublimation point of somewhere in the neighborhood of minus 78-ish degrees Celsius. Typically what we do is we take that solid carbon dioxide, the dry ice, and we put it in a particular solvent. For instance, if I put dry ice in isopropyl alcohol, which is rubbing alcohol, I can create a slush of about minus 78 degrees. So it's very easy to form liquefied ammonia. The only thing you have to be careful of is once you liquefy a gas, you have to keep it cold, because if it warms up, it'll expand very rapidly and end up exploding. So very easy to make liquefied ammonia. And once you make liquefied ammonia, if you add sodium metal to it, what you end up doing is forming what is called the solvated electron. Okay, you end up forming that solvated electron by just dissolving sodium metal in liquefied ammonia. So what happens is sodium metal has one unpaired electron, and when it goes into liquid ammonia, it basically becomes a sodium ion and an electron that can go around the solution. This is a pretty spectacular reaction. It forms a very dark blue color, and this is the ultimate in doing reduction, right? Because remember, reduction is gain electrons. So if you have a naked electron, which is essentially what this is, that is the purest form of reduction. So what happens in this case is that the sodium metal loses its electron and forms what's called a solvated electron in the liquefied ammonia, and that's what causes the reaction to occur. Now, this is a mechanism that I'm not going to ask you to reproduce, but again, what I like to do is to give you an idea of how the reaction occurs so that if nothing else, if you're stuck and you say, well, I'm wondering, wait, what is the stereochemistry of this? Maybe if you remember, oh, okay, it's got that solvated electron, it'll always end up with a trans mechanism. So here's what happens. What happens is that the solvated electron adds to this carbon, and then the pair of electrons in the triple bond goes to the carbon. So these arrows are a little bit fuzzy, but this is a full-blown arrow, whereas this is our fishhook arrow that we saw in the anti-Markovnikov edition, and we'll see in the next lecture video as well. So that leaves this carbon with an unpaired electron and this carbon with a pair of electrons and a negative charge. This is what's called a radical anion, because it's got a radical part and an anion part. Now the critical part of this is that these are big clouds of electron density, right? And so when this electron adds to the triple bond, these two electron clouds have to be trans to one another because they're big clouds of negative charge. They want to get away from each other as much as possible. Once you have the anion, then you have a C minus. That C minus is a stronger base than N minus, so it just simply deprotonates the ammonia so that I end up with a vinyl radical now. So the C minus deprotonates and we end up with NH2 minus. Once I form this vinyl radical, then what happens is then the unsolvated electron, a second one adds to make this an anion, and now that anion then deprotonates another ammonia molecule, so that in the end the two hydrogens had to add trans. Okay, so the key part of this is this intermediate right here, where the radical anion has to have the two lobes trans because they're repelling each other, and that sets the stereochemistry up for the two hydrogens to add trans. Okay, so that is the mechanism for doing reductions of the double bond to form the trans alkene. So just to take a step back before we go to the final topic for alkynes, if you want to reduce an alkyne all the way down to the alkane, use hydrogen and unpoisoned palladium or platinum. If you want to stop at the cis alkene, poison the palladium catalyst and make the Lindlar catalyst. And then finally, if you want to make the trans alkene, go ahead and use sodium and liquid ammonia, and that will form the trans alkene. Okay, so we've got a lot of variations here, which is important because in order for me to be able to do my maximum number of reactions, I need to know, or I need all the reactions to make the maximum amount of molecules that I can make. Okay, the final reaction that we're going to talk about is hydration. So we're going to take in this case, our terminal alkyne, and we're going to add to it H plus H2O. And in this case, what we're going to end up making is a ketone. And you might say, that's not what I predicted. You're absolutely right. That's not what you predicted. So what happens? So in this mechanism, here's what happens. I'm going to react. The H plus is going to be bonded by the terminal carbon here with the most hydrogens, taking its pair of electrons to bond the carbon, or bond the hydrogen. So now I'm going to end up with my vanillic carbocation. So now I've added two hydrogens. What happens next? Water, the entire water molecule comes in and adds to the carbocation. So far nothing's new. I've added my water to the carbocation, and then my water is going to catch the hydrogen as the pair of electrons goes back to the oxygen. So I'm going to basically lose this as an H plus to be captured by the water. And so I'm going to make this molecule as the final product plus H3O plus. Now, this molecule is not this one. So what happens? Well, this is actually a molecule called an enol. Why is it called an enol? Because it's half alkene, half alcohol. Enols, for the most part, are unstable. They tend to be very unstable, particularly ones that are just simple like this one. This would be the enol of acetone. And I don't know that anybody's ever actually gotten to isolate the enol of acetone. But they're very unstable. And what they do is they undergo an equilibrium reaction. So in this case, what would happen is that my enol would undergo the following reaction. And this is an equilibrium reaction. So what I would do is bring this pair of electrons down to form the carbon-oxygen double bond, and then break this carbon-oxygen double bond and use that pair of electrons to bond this hydrogen. So that hydrogen is going to shift from being on the oxygen to being on this carbon. And so what that ends up doing is that ends up forming then the carbon-oxygen double bond, and then adds the hydrogen to the other carbon in the double bond. And so this would be a ketone. So there is an equilibrium between a ketone and an enol. It's called the keto-enol equilibrium. This reaction is not any kind of resonance structure. The reason it's not a resonance structure is because I broke this bond and I formed a new bond. Right? I formed that bond and I formed this new bond. This is what is called a tautomerism. And a tautomerism equilibrium is one where it is the simultaneous movement of a hydrogen atom and electrons. So when you have the simultaneous movement of a hydrogen atom and of electrons, primarily the multiple bond, the pi electrons, so I should probably say and pi electrons, when you have the simultaneous movement of hydrogen atom and pi electrons, that is what is called tautomerism. So while these look like they could be resonance structures, trust me, they are not. So run-of-the-mill simple enols are very unstable and immediately form ketones. As a matter of fact, this one, I don't know, it's probably only been within the last, let's say, 10 or 15 years that anybody's gotten a structure of enol, of the enol of acetone, because it is so unstable. So if you go on to be a chemistry major here at John Carroll and you take physical chemistry lab, you'll do an experiment where we look at the equilibrium constant between the ketone and the enol form. And actually, Dr. Weiner and I have done some studies on this and published a paper on a sort of variation of this. And in one of the referees' comments, they did make a statement. They're like, well, in these resonance structures, and we finally got a chance to say, remember, those aren't resonance structures, they are tautomers. So that's common. That's sometimes a common misconception. But enol is formed, then it immediately forms the ketone. So that's why this product is different, is because the enol tautomerizes to form the ketone. And that will happen in this class all the time. Okay? So if we use a terminal alkyne, we're always going to get Markovnikov addition to form the ketone. Now, if you're kind of thinking, could we do anti-Markovnikov addition? Because if we did anti-Markovnikov addition, we would end up converting the end carbons to a C double bond O, and we could make an aldehyde out of the triple bond. That would be nice, be useful on some occasions. So how would you do anti-Markovnikov addition? Well, the way you would do anti-Markovnikov addition would be to look at this and say, oh, I just need to add an H and an OH anti-Markovnikov. Now, what reagent in the last series of alkene reactions did we use to add H and OH anti-Markovnikov? Hopefully everybody's yelling at their screen. BH3, H2O2. That's what we use to add to do anti-Markovnikov addition. Well, there's a problem with just using BH3. And that is, remember where the BH3, when the boron would add to one carbon and the hydrogen would add to the other carbon. And remember, the boron added to the least hindered carbon, which is the one with the most hydrogens. And then the hydrogen peroxide came in and converted that boron into the OH group. Well, the problem with a carbon-carbon triple bond is it has a linear geometry, so distinguishing the steric hindrance between these two carbons is kind of difficult. If we just used BH3, which you could write down on a quiz or an exam, I'd accept it. But in the lab, it would not work all that well. And the reason for that is quite simple, because these two carbons, it's kind of hard to distinguish sterically which one is more or less. There's not that much difference in this linear geometry. So then we go back and we take a rule, or we take a page out of the tertiary butoxide playbook. And you're like, what are you talking about? Well, remember that when we were talking about the difficulties in using alkoxides as bases, we said, well, they could act as bases or they could act as nucleophiles. And certainly methoxide or ethoxide has this problem, and we talked about that in the last lecture video where we were talking about SN1 versus, or SN2 versus E2. And we certainly ran into that problem with the top hat reaction chart. But when we first started talking about this and said, hey, I would like to focus on an alkoxide just being a base, what did we do? We said, let's make it tertiary butoxide. So what did I do? I made this alkoxide sterically hindered so that it wouldn't act as a nucleophile. It would just act as a base. So that's what I mean by taking a page out of that playbook. If this is sterically unhindered, let's make this guy sterically hindered and force it to add to the end, to add to the terminal carbon. Okay, is there a reagent for that? There's actually a number of reagents for that. This is one. This is disecondary isoamyl borane. Oh, that is a horrible, horrible name because it violates so many IUPAC rules. Isoamyl is the older terminology for pentyl, so it would be isopentyl. Disecondary, the IUPAC gods would be shuddering right now. But disecondary isoamyl basically means that it's like the boron's attached to the secondary carbon of an isoamyl, but if it was truly isoamyl or isopentyl, the connection would be here. Yuck. But that's what it's called. It's called SiA2BH because there's two of these groups and they are disecondary isoamyls. Anyway, these are sterically bulky groups, as you can kind of see in this picture over here. And so now what I do is now I make my boron, number one, it only has one hydrogen that it can add, but number two, it's sterically hindered. So now it's going to force that boron to add to the terminal carbon. So now when I have my boron with my hydrogen and my disecondary isoamyl group, now when this goes ahead and does the reaction where the hydrogen comes here, we go through our four-member transition state to make it cis. I'd add the hydrogen on this side. I would have the boron with the diisoamyl groups. But it forces the boron to add to the terminal carbon. And then what happens? Then we treat this with hydrogen peroxide, and the hydrogen peroxide comes in and it replaces the boron with an OH group. So now we have our enol, and now that we have our enol, we can go ahead and do our tautomerism equilibrium to now give us the aldehyde. And so if you want to do anti-Markovnikov addition and form an aldehyde, this is a reagent that you can use. There are others listed in Top Hat. I believe 9BBN is another one of those reagents. Basically, they just put the boron in the middle of a bicyclic ring. So there's lots of ways to do this, but my focus is on some of these basic principles that we've used this semester in terms of thinking, okay, if I want to take advantage of steric hindrance and my one reagent isn't sterically hindered, make the other one sterically hindered so that way I can go ahead and add, take advantage of steric hindrance. And that's exactly what the SiA2BH does, or 9BBN does as well. So that's how we can do anti-Markovnikov hydration. So a new concept of enol, of tautomerization, but in essence, what I'm doing is I'm just hydrating the double bond or triple bond, and then the enol's unstable and then tautomerizes to the aldehyde. Okay. All right, so that is the end of alkynes. So in terms of reactions of alkynes, we basically have the same types of reactions as we had for alkenes, except we could do two equivalents. Well, not in the case of hydration. That was kind of a brand new reaction. And the reductions, there were three options, two of which we had seen before. Cis-hydrogenation with a poisoned palladium catalyst to form the cis-alkene, and then using a very active palladium platinum metal catalyst, you would go all the way down to the alkane, and then a new reaction of sodium with liquid ammonia to then form the trans alkene. So alkynes, hopefully you remember enough about the Alkyne reaction so that there's nothing really new here except hydration and reduction. And finally, cleavage. Remember, to cleave a triple bond, I need the most potent oxidizer I can get, and that'll cleave the triple bond. But it'll leave two carboxylic acids behind. Okay? So we have one more topic left for this semester, and that is free radical halogenation. And that's going to be in Chapter 18 of the Top Hat textbook, but typically it's done first semester. So that's going to be our final topic of the semester. So that's what we will do in the next lecture video.